Okay. Are you ready?
Yes, Captain.
Yeah. Are you full of desire to start?
Yeah.
Sure.
Well, okay. You should prepare 2 balls for the blood dropping from your ears, and 1 additional ball for the blood dropping from your eyes, because my handwritings are awful. Okay, let me...
We got used to the handwriting of other teachers and professors.
Okay, you know, there is a competition who has the worst handwritings in the world. We're trying to win. Okay.
I think I will win in the competition of worst handwriting.
We'll see. We'll see. Okay. You know, probably you have the talent to write awful, but I have the experience, you see, like 15 years of awful handwriting. It helps me a lot. Okay, so let me explain the goal for the seminar. So during the lecture, I gave you the definition of the group. So this is one of the main objects in algebra. So we will encounter this object like here and there all the time. So here today, we want to learn several examples and to learn how to deal with them, like how to answer different questions, what kind of questions we might ask. So we want to start computing some stuff in order to get used to the definition. So, okay. Let me start with a simple question, just for the beginning. So suppose we have a finite set. Is X is a set, and suppose X consists of finitely many elements, like 1 to n. How many binary operations do we have? So a binary operation is a map from x times x to x. So how many binary operations do we have?
Maybe like n squared.
Again?
Maybe like n squared, because we need to specify n squared positions.
Probably n cubed. Oh, wait.
Maybe n choose 2.
Okay, here is the answer in the chat. So let me recall all the possibilities we have.
Yeah.
So n squared, the second option was n cubed. Here in the chat, we have n to the n squared. What are other options?
N choose 2.
N choose 2. Okay, or in the different notations. Okay, what are other options? Okay, let's vote. You know, math is a social science. So how to solve problems in the social science? We should vote.
But actually, math is not a place for democracy. In such
no, it's actually a social science. No, really, guys, it's a social science. Let's vote. So and see which option wins. So write in the chat 1 if you vote for the first option, 2 if you vote for the second option, and so on. I just want to see what. Okay. Oh, come on. I see. You see, it's math is a social math. It's a social science. So we can prove anything just by voting. You see? So here we prove that the third option is the right one. So let's try to understand why. So, okay, but you see there are two guys who don't see why this is true. So let me recall. If you have a function from a set A to a set B, then, okay, if you have two sets, A and B, two finite sets. So how do you compute the amount of functions between A and B? So here, list all elements here. For example, you have n elements in A. Then you may take the first element to any element of B. Then you may take second element to any element of B, and so on. And all options are valid. So, you have m options for the first element, m options for the second element, and here you have n elements. So there are m to the n options for all possible maps. And here, the binary operation is a map from this set to this set. So we just count the amount of elements in X, which is n, and then count the amount of elements here, which is the amount of pairs, which is n squared, and we raise the amount of elements here to the power of amounts of elements here. That's it. Yeah, here is the right answer in the chat. Do you have any questions? Yeah, and guys, please, could you turn off your mics while you're not speaking? Okay, now, let me recall you what the permutation is. So, do you remember what the permutation is, by the way? Who doesn't? Are there people who need?
Permutation is swapping element.
Okay. Okay. Just in case, I'll remind you. Permutations. So I'll fix the set of elements from 1 to n. And a permutation is a bijection on this set. So permutation is a rule which takes each number to a uniquely determined number. Well, where we given numbers from 1 to n. So it's effectively just permutes the order of these elements. So, for example, it takes 1. How do you define permutations? I mean, how do you construct permutations? You usually do it with the tables, where at the first line you write the arguments, and at the second line you write the image of your arguments. So like this. And if you want me to give a concrete example, for example, we're given 4 elements, we can do something like that. So this is a permutation on the set of 4 elements, which takes 1 to 2, 2 to 1, 3 to 4, 4 to 3. Is that okay, or you need some other explanations, or are there any questions? Okay, the set of all permutations on n elements is denoted by Sn. This is the set of all permutations on n elements. Okay, but we're not interested in sets. Like pure sets are the object for discrete math. Here in algebra, we want to find a binary operation on this set, and we have one, which is composition. So if we are given 2 different permutations, sigma and tau, so there is a product which is a composition, which means if I want to compute, okay, what does it mean? Ilya Rashkov?
It was an accident.
Okay, just in case. So it just defined in this way, but if you want to think of it graphically, so you have this set, first you apply sigma, and second you apply tau. This is the composition. Now we have this binary operation. So yeah, and just in case k goes to sigma of k, and after that it goes to tau sigma of k. So I claim that the set of all permutations on m elements with this operation is a group. Let's verify that. So the claim is Sn with this composition is a group. Who sees that? Okay. Okay. Is there anyone who doesn't see this? Just write minus in the chat if you don't see this. Okay, then what is the identity element? What is the neutral element? Oh, okay, I said it, identity, yeah, identity map. Okay, if I'm given a permutation like this one, what is the inverse?
We put the image in the first row and the arguments in the second row.
We swap the lines. Yeah. Okay, that's cool that you know this. Okay, that's nice. Do you know what the sign of a permutation?
Yeah.
Okay. Do you know? So if you remember, there is one characteristic which is called sign. So all permutations are divided into odd and even. Yeah, it's -1 to some power, and the power is
P
computed
plus Q.
using your permutation. So if you consider all the permutations, so you can divide them into groups. The even permutations and odd permutations. So even permutations have a special name. They're denoted by the letter capital A with index n. So this is the set of all even permutations. Even permutations inside of all permutations. Okay. Let's could you let me ask you another question? So we know that Sn is a group. Is it commutative or not? No, no.
No, it's not.
Okay. Are there any other thoughts regarding this question? Well, actually, it's sometimes commutative. Because you have this parameter n, it may change. There are actually two cases when this group is commutative. If n is equal to 1 or 2, then this group is commutative. Because if you have permutations on one element, they consist only of one element, which is ID. And this is a commutative group because it doesn't matter how you multiply ID with ID, you always get the ID, so the result will be the same. The second option is the permutations on two elements. The group consists of ID and the transposition. So this group is also commutative. But the groups Sn with n is greater or equal than 3 is not commutative. Could you give an example of a pair of elements that do not commute?
For example, all zeros.
Again?
If we consider like structures that will contain only zeros, they will not compute. No.
No. The permutation. So let me make it easier. I want you to find two permutations. So this will be a sigma, and this will be a tau. So I want you to fill the second rows. So could you find the permutations sigma and tau such that the product on the left-hand side is not equal to the product on the right-hand side? Just write down the second lines in the chat or just name them. Okay, let's check. 3 to 1 and 2, 1, 3. 3, 1, 2. Okay. 3, 1, 2 and 2, 1, 3. And here 2, 1, 3, 3, 1, 2. Let's check. I used, I'm sorry, I confused two different answers. Okay, let's check what's written here. So 3 goes to 2, 2 goes to 1, 3 goes to 3, 3. Okay, this one is already a working example. So this is the example. Do you have any questions regarding this example? Okay, but be careful. So sometimes this group is commutative if n is sufficiently small. Okay, let's check some properties of different operations. For example, I gave you an example of an operation which is taking maximum on integers. And we have 4 properties: associativity, the existence of a neutral element, the invertibility of each element, and commutativity. So is this operation associative? So we take pair A and B to the maximum of A and B. Is this operation associative?
Yes, it is.
Okay. Do you have any other option? Okay, yes, it's associative. The second, does it have a neutral element? Is there a neutral element? Okay, we have 2 options, yes and no. If you say yes, then please show me this neutral element. Name me explicitly which integer plays the role of the neutral element. So yeah, all integers. Okay, no neutral. I agree with me that there is no neutral element. Okay, so why there is no neutral element? Because what does it mean that you have a neutral element? So if there is such a neutral element here, it means that maximum of A and E equals A, and maximum for E and A equals A for all integers. If you suppose that E is some specific number, then take A to be smaller than E, then the maximum between A and E will be E and not A. So there is no such an integer E. Andrei, I do not understand your claim. It must be mine Z. What do you mean?
I think he meant like minimum of Z.
What again?
Minimum number maybe he meant.
There
I'm
should
not
be a
sure.
minimal element in Z, which is.
But there is no minimal element in
yes.
Z.
So.
Yeah, that's exactly
okay.
the explanation. Yeah, okay, that's true. So since there is no neutral element, by the way, are there any questions regarding this? Okay, so since there is no neutral element, it doesn't make sense to discuss the inverse elements. And of course, it's commutative. I believe it's clear. So it doesn't matter the arguments in the maximum function. So you cannot make a group out of this operation. Okay, let's pass to the other example. By the way, it's probably better to switch here to the second column. It will be easier to read. So I will also share all the whiteboards I use, so you will be able to read them anytime you wish, so for convenience. So don't worry, everything what I'm writing is not lost in space and time. Okay, so let's discuss this group. So usually we just skip the name of the operation plus and just simply write Zn, assuming that the addition is the operation used here. So, and I recall that this is the set of all integers smaller, of all natural numbers smaller than n, and the operation here is by definition operation modulo integer number. So the neutral element here is 0. I hope it's clear. And if you're given an element, what is the inverse element?
N minus A, you said?
Yeah. N minus A. Well, in case A is not 0. In case A is 0, it's just simply 0. Because n minus 0 doesn't belong to this set if A is 0. So yeah, this is the inverse element. And associativity, I believe you proved it during the discrete math course. So now let's take some specific number, for example, say 6. So we take Z6. It consists of 6 elements. And let's compute the orders of all elements here. Okay? Do you remember the definition of the order of an element? Should I recall it? Well, okay, Anton. It was shown that the order of the element coincides with the amount of elements in the cyclic subgroup generated by the element. But by definition, the order of an element in multiplicative notation was the least possible positive natural number, such that g to the n equals 1, or infinity if there is no such n. And in additive notation, and here we use additive notation, just in case I want to repeat the definition, so it's the least possible positive natural number such that ng equals 0 or infinity if there is no such n. So these are two different notations. This is the multiplicative notation and this is the additive notation. So this means we apply operation n times, and this also means that we apply the operation n times. Okay, but since here we use addition, so if we add a number n times, it means that you multiply it by the natural number n. So that's why this notation works like this. So let's compute the orders of the element. So what is the order of 0? One. Are there any other options? Any other versions? Okay, yeah. The order of 0 is 1. Why? Because, well, this is the least possible positive integer, and zero is the first power of the neutral element is the neutral element. So, yep. So what is the order of element 1? Okay, 6. Good. By the way, is it clear to for everyone? Should I explain this? Okay. Just in case. So how do you check that? You just take 1 and start considering its powers. Its second power is 2. Next power is 3. So next power is 3 plus 1 is 4. The next power 4 plus 1 is 5. Next power 5 plus 1 is 6, which is 0 modulo 6. And that means that this is the first power, which is 0. Okay, so 6 is the order of the element. What is the order of 2? Yep, it's 3. So you add 2 3 times, and this is the first time when you will get 0. Now, what is the order of 3? Yep. Oops, rewrite it. What is the order of 4? Okay. And what is the order of 5? Six. Okay. Just in case, I don't know how you compute that, but the way I think about this is the following. So 5 is the same thing as -1 in Z6. Okay. So so this is just the inverse element for the element 1. And here is the rule. The order of element is the same as the order of its inverse element. Or in additive notation, the order of element is the same as the order of its inverse element. Okay? So,
could you explain one more
it's not
time, please, why the values are exactly these?
So I should explain why this equality holds.
No, previously. Why, for
Why
example,
5
order
is,
of 2 is 3?
Why order of 2 is 3? Okay, no problem. let me write down the computation here. So by the definition, what is the order of 2? So you consider 2 plus 2 plus 2 plus 2 k times, okay? Where k is at least 1. And you find the least possible k when it becomes 0. So 2 is not 0, okay?
Ah, okay, I see now.
2 plus 2 is 4, is not 0.
Mm-hmm.
And 2 plus 2 plus 2, yeah, it's 6, which is 0. So 3 is the first time when you get 0.
Yeah, okay, thanks.
Mm-hmm. So now I want to discuss this property. So the order of the element is the same as the order of the inverse element. Who sees that? Oh, I think, okay, who can explain this? Okay, 1 plus. Okay, that's a good explanation, Andrei. By the way, Andrei posted in the chat actually the proof of this claim for the additive notation. Is there anyone who doesn't understand why this line implies this equality? Should I explain that? Okay, so it's clear to everyone. Yes, me. Okay, so it's clear to everyone. Okay, so now using this property, you see, if you can, so usually if you have some elements, the other half will be the inverses for the first half. So the inverse element, let's try to find the inverse elements for everyone, for each element. So what is the inverse for 0? 0. So it's inverse to itself. What is the inverse for 1? Well, I wrote it. It's actually 5. So, and the inverse for 5 is 1. What is the inverse for 2? Yeah, it's 4. And the inverse for 3, it's again 3. So here we have 5 equals minus 1. 4 equals minus 2, and 3 equals minus 3. Well, actually, also we have 2 equals minus 4, and 1 equals minus 5. So if you computed the orders of 0, 1, 2, and 3, now you can compute the orders of 4 and 5 using this rule below. So you don't need to compute the order of 4. So it's simple here, and you can do it by hands, but since you already know that the order of 2 is 3 and 4 is minus 2, then the order of 4 is also 3. So this is one way how to simplify the computations. Okay. So let's try a different example of a group. Now, let's take prime number 7 and consider Z7 star. I recall you, this is all the elements from Z7 which are co-prime with 7. Could you describe me this set explicitly? What are the elements here?
2, 3, 4, 5.
Again, 2, 3, 4, 5?
Yes, 6.
2, 3, 4, 5.
And 1
6.
also.
And
no,
1.
not 7, but 6.
Oh, sorry. Yeah, that was by accident. And 1. Yeah, all non-zero numbers. Well, actually, for any prime number, if P is prime, then ZP star consists of all non-zero elements. So you just exclude the 0 element from ZP. Because since P is prime, all elements strictly smaller than P are co-prime with P if they are not 0. So only 0 is not co-prime with a prime number. So, okay, now I claim that Z7 star is a group. This is with multiplication modulo 7. So so for any two elements A and B here, I write A times B means A times B mod 7. So it first multiply and then takes model 7. So is it clear that this set with this operation is a group, or should I explain this? Oh, do you know the fact that this is a field? Did you learn that through the discrete math course? Or okay, is there anyone who doesn't understand that? Oh, in linear algebra, you know that. Okay, cool. Okay, then it's perfect. So, okay, so just in case, if you want me to repeat the reasons why this is a group, just tell me, I'll repeat. But if not, then it's perfectly fine. I mean, if you already know the fact, then it's simpler for me. So this is the group. What is the neutral element of this group? Okay, 1. Now, so we have these elements 2, 3, 4, 5, 6. Please find me the inverse elements. What is the inverse element for 2? Six. 6 times 2 is, I'm not sure. Why 6? By the way, is it clear what you should do? Should I explain the task?
We should prove that this is a group finding all the inverse elements of for every element.
Yeah, we should, okay. Yeah, we should find all, well, I mean, I assume that we already know that this is a group. And since it's a group, each element has its inverse element. So I want to compute explicitly the inverse element of each element. So here is another version, which is 4. That the inverse for 2 is 4. Well, let's check. How to check? We multiply 2 and 4 and take the result modulo 7. 2 times 4 is 8, and modulo 7, it's 1. Yay. That's the win. So 2 times 4 is 1, modulo 7, that means that 4 is the inverse for the element 2. And this automatically means that the inverse for the element 4 is 2. No, I'm not asking you to prove that ZP is a field. I'm just asking to compute the inverse element for each element from 2 to 6. Oh, okay. Okay, I see. So what is the inverse for the element 3? Yep, it's 5. So the inverse for the element 5 is 3. What is the inverse for the element 6? It's 6. Well, let me explain why you don't need to compute anything here, because the inverse for the neutral element is itself. The inverse for 2 is 4 and vice versa. The inverse for 3, oh, I'm writing 7 again. I don't know what this means today, but okay. Oops. So all elements split it into pairs. So since 6 has only one option for the pair itself, so 6 must be the inverse for himself. So since we computed all the previous elements, we don't need to compute the inverse for the element 6, because now we know that it's automatically must be 6. But you can easily check that. Okay. 0 is not in the set. Yeah, 0 is not in the set. There is no 0 here. 0 doesn't have inverse with respect to this operation. Okay.
Then is ZP star a field?
No, ZP star is not a field. It's a group. It's not closed under addition. ZP is a field. So
okay, now I see. Okay.
Yeah, because there is no such a thing like 1 plus 6 is 0 in Z7, and there is no 0 in Z7 star. Okay. If you have any question regarding this example, please ask. If not, I will proceed to the next one. Okay. Do we have? Yeah, we have some space here. So the next example is, well, the group of non-degenerate matrices, GLN over R. So this is the set of matrices with non-zero determinant. Well, the first question I want to make, is it a group? The set of non-degenerate matrices with addition, is it a group? Is this thing a group or not? Why? Okay, let's check. First of all, the addition of matrices is associative. We know that. Yep. Okay, but what you have to check 3 properties. First, associativity. Check. Second, oh, that's not the associative. Check. The second, neutral element. What is the neutral element here?
Zero matrix.
Okay. Does it belong to the set?
No.
No, it doesn't belong to the set. It's not a group. Yeah, that's important. Also, the addition is not well-defined operation here. If you take a matrix A, which is non-degenerate, and you add it with minus A, you will get 0, which is degenerate matrix. So the addition is not well-defined. The addition is not well-defined. You see, that was a trap here. First of all, you should check if the operation is well-defined on your set. So here, this is the problem. It's not well-defined. You cannot find a set of arbitrary non-degenerate matrices and, well, inside the non-degenerate matrices. The result might be 0, for example, like here. Yeah, it's a trap. Yeah, but not that kind of trap. Okay, but now let's try GLN of R with multiplication. Is this a group? Or is this a trap again? So yeah, what is the identity element here? Yeah, it looks like a group, but is it? Yeah, the identity matrix. The identity matrix is a neutral element. Now, if you are given a matrix A, the inverse matrix is the usual A to the power of -1, the usual inverse matrix. And yes, the operation is well defined. The product of non-degenerate matrices is a non-degenerate matrix because determinant of A times B is equal to that A times that B. So first of all, well, actually, let me discuss the order of verification. First of all, you should check that the operation is well defined. So the operation actually determines a map from the set of all pairs to your set. So the first thing you should check that if you take arbitrary elements from your set, you apply your operation, the result is always inside your set. That's the first thing you should check. And this is how we check it. So the determinant of the product, we know how to compute it. So if this is not 0, then the left-hand side is also not 0. Then, because if this is not true, then you don't have an operation. So you don't have the piece of data for the definition of a group. So so you can prove that this is not a group even earlier before you check the axioms. You don't have the required data to produce your group because you need a set of elements and the operation. And since there is no operation, so you cannot define a group. That's what happened in the previous example. And then you check all the axioms. So it's associative, you have neutral element, and every element is invertible. Okay, what about this example? The set of all matrices with addition. Is it a group? Okay, yes, it's a group. So the neutral element, so the addition matrices are filled. No, matrices do not form a field. Field must be commutative, first of all. But the matrices are not commutative. But even more, field must contain no zero divisors, and matrices contains a lot of zero divisors. That's okay. That's what algebra for. It's supposed to kill your brain. I mean, if you go to the Wikipedia page and see what the algebra is, it's literally written like algebra is a part of math which is created for people to suffer, for make people suffering. That's it. That's the only reason, no joke. That's why people invented algebra, to kill your brain. Okay. So, okay, again, now, first of all, the operation is well defined. The sum of all pair of matrices, again, is a matrix. And the neutral element is 0. And the inverse element is -a for each matrix A. And the operation is associative. Now, the next example. If I take GLN of R, not GLN, all matrices with multiplication. Is this a group? Why? The answer was no, but why? Yep, not all matrices are invertible. Yep, no, it's associative. It's associative, but not all matrices are invertible. The zero matrix is not invertible. That's the right answer. Okay. So, and what about this example? I take all rational numbers with multiplication. Is it a group? No, it's not a group. Yeah, again, it's not a group. But what if I exclude the zero number? Then, is this a group? There are two different answers. Andrei thinks that this is a group, and Alexander thinks the opposite. Yeah, multiplication, yeah. Okay, Then yes, I hope it's clear to everyone. But what if I do the same trick with matrices? Let's try to exclude the zero matrix. Is this a group? Yeah, true. Yeah. In order to make this example to work, we have to exclude all degenerate matrices, and then we will get GLN. And for GLN, of course, we know that it's a group. Yeah, okay, that's fine. That's perfectly fine. So let's proceed to, yeah, if you have any questions regarding the stuff what haven't yet, so please ask, and if not, I will proceed. Okay, so now let's list all the elements of the group S3. How many elements are here? S3 is the group of all permutations on freedom. Yeah, 6. What are they? By the way, do you know what the cycle is in terms of permutations? Okay, then yep, or not?
Yeah, we know.
Oh, you know. Because I was told that you didn't learn this stuff during linear algebra, so, but just in case. So here you have ID, then you have permutation 1, 2. Is it clear what it means? Okay, let me write down the elements here, and then I will explain if something is not clear. So yeah, so the element here, 1, 2, means that it's a permutation which takes 1 to 2, 2 to 1, and the element 3 left untouched. So this thing, it leaves 1 as it is and switch 2 and 3. This switch 1 and 3, and this works in a bit different manner. It takes 1 to 2, 2 to 3, 3 to 1, and this one takes 3 to 2, 2 to 1, and 1 to 3. So just in case, so it works like this.
Yeah, we know it. We had it in the first module, as far as I remember.
Oh, okay. But just in case if someone has any questions regarding this notation, just ask. If not, then I will proceed. Okay, let's try to compute some subgroups here. Okay? So a subgroup is a subset in S3 which obeys several rules. Do you remember the rules? Yeah, it must be closed under the operation. So if X and Y are an H, then their product must be an H. It contains neutral element. Yeah, the ID must be an H. And close under the inverse. Yeah. Good. So these are the properties. So there are always 2 trivial subgroups. Trivial, this is just the name. So if I can form a subgroup just by the identity element, this is the smallest possible subgroup. It's closed under multiplication. It contains identity. It has inverse for each element. So the inverse of the identity is identity. So this is an example of a subgroup. There is another trivial subgroup, which is the whole set. This is the largest possible subgroup in S3. Well, these 2 examples work for any group. So let's try to find other subgroups. Can you find at least one subgroup different from these 2? Let's start with just one example. Could you find at least one subgroup different from these 2 trivial ones? Cool, even permutations. Yeah. But could you name explicitly the elements of this subgroup? So let me. Okay, there is another example. Yeah. So the guys came up with two examples. So let me call it the example 1, the example 2, the example 3. The example 3 was A3, which is even permutations. And what are the even permutations? Well, it's actually ID. Tell me, the transposition 1, 2, is it even or odd? Odd, so it's not even. So 2, 3, it's also odd. 1, 3 is also odd. And these two guys are actually even. 1 to 3, cycles 1 to 3 and 3 to 1 are even. So even permutations consist of these 3 elements. Okay. Now, the fourth example was ID and 1, 2. Are there any other groups? Can you find all the subgroups? Because you see, this is a finite set. There are only 6 elements, so there are finitely many subsets. So there are finitely many subgroups. Some of the subsets are subgroups, some are not. So we can just list all of them and just find all the subgroups. But can you do this just right now? What are other subgroups? And by the way, the set ID 1, 2, and 2, 3. Is it a subgroup? No, why? Well, there is no general way to compute the amount of subgroups. Well, actually, there are Sylow theorems which says something regarding the amount of subgroups, but that's more or less, we will not study them. It's a very advanced technique, and it's a very complicated story. For example, well, it's sometimes, well, it depends on the operation. If the operation is terrible, you may have a very few subgroups. If an operation is really good, you may have a lot of subgroups, and it may happen on the same set of the same power. So it's very complicated question. So that's why we just consider examples and computing all the subgroups by hands. Well, there are some tools, but they are very advanced and they do not answer to this question in the most general case. But there are some specific classes of groups which we will discuss later, and for them we will see the tools. Andrei, do you mean the Sylow subgroups technique? Well, okay. I'll probably tell you a couple of words about these results, but this won't be in our course officially. By the way, is this true? No, it's not true. No. That was suggested. But what is the right answer? Let's check. How does it work? So let's compute it as a table. 1, 2, 3. How to compute where something goes? Yeah, the later one is the right answer. So it will be 1, 2, 3 cycle, which takes 1 to 2, 2 to 3, 3 to 1. So how do we compute this? So you take one. Where does it go by the action of the second permutation? One goes to one, and by the action of this one, it goes to two. So the composition takes 1 to 2. Then, if you take 2, apply this guy, 2 goes to 3. Apply this guy, 3 stays the same. So 2 goes to 3. Now, if you take 3, 3 goes to 2 by the action of this guy, and 2 goes to 1 by the action of this guy. So after 2 steps, 3 goes to 1. That's how you compute. And this is exactly the cycle 1, 2, 3. So that's why this guy is not a subgroup, because this times this does not belong to this subset. So, okay, right, so this is not a subgroup. So right now we have these 4 examples. Are there any other examples of subgroups? Let me switch like that. Could you name me any other subgroup? For example, 5 and 6. Empty group is not a group. Why? Yep, no neutral element. Empty subset is not a subgroup because it doesn't have a neutral element. Yep. So it's never true that empty subset is a subgroup. But come on, what are the other options for the subgroup here? Let me tell you some hint. Look at the example number 4. Yeah, you can produce 2 subgroups in a similar manner. ID 2, 3 and ID 1, 3. Yeah. What are the other subgroups? Are there any other ones? Yeah, I would like to discuss this, but probably let's discuss this now. So what Andrei told us, that this is the cyclic subgroup generated by the element 2, 3. This is the cyclic subgroup generated by the element 1, 3. This is the cyclic subgroup generated by the element 1, 2. And actually A3, let me write it here, is the cyclic subgroup generated by 1, 2, 3, by the cycle 1, 2, 3. So the example 3, 4, 5, and 6 are the examples of the cyclic subgroups. So if you want to produce an example of a subgroup, the first thing you should do is to consider all possible elements and generate the cyclic subgroups for these elements. These will be your first kind of examples. So, and here, if I take these 3 elements, they generate 3 distinct subgroups. If you take these or these element, they generate the same cyclic subgroup, which is this, because this inverse to this one is this one. They are inverse to each other. And actually, there is no other options. These are all subgroups. No, it's not an equivalence relation. It's like implication relation, because generate the same cyclic subgroup is an equivalence relation, but not belonging to the same cyclic subgroup. Okay, so does anyone need an explanation why these are all possible subgroups, why there are no other subgroups? Who wants to see the explanation? Okay, so suppose there is a subgroup. So let me do it like here, because I don't need a lot of space. So let's H be a subgroup. So if it contains only the identity element, this is the first case. So we may assume that it contains something else. So there is some sigma, which is not identity, which is in H. Now, there are 5 options for this sigma. It's either these elements, these, or this. Okay? Let's consider the first case. So suppose that 1, 2 is in our group, H. But then the whole cyclic subgroup must be in our H. Just by definition of the subgroup, because it contains all the powers of the element 1, 2, positive and negative. So if subgroup contains an element, it contains its cyclic subgroup. Okay?
Excuse me, is it is a subset or belongs to the last sign?
It belongs to, because it's a subset. So this guy is a subset of this guy. Did I say belong?
No, I just wanted to understand. Thank you.
No. If you want to say belong, which is this sign, it means that the left-hand side must be an element of the set. But here, the left-hand side is a subset. So it's just a part of R. Okay. So it consists of elements. So it's just a part here. So now, here we have 2 options. Here, it's either equality or not. So if it's equality, then this is the example number 4. You see? Okay. And here we consider the case where sigma was this element. So in the analogous way, considering other cases, we have the same situation. The corresponding cyclic subgroup of the element is a subset of H. And if it's equality, then this is one of these cases, 3, 4, 5, or 6. So now we want to consider the other option when our subgroup H contains one of these 4 subgroups and strictly contains them. Are you with me now? Should I repeat something, or was something not clear? Okay, so I believe
I still don't understand why the span of 1, 2, the generated, is a subset of H. H is
okay. Okay.
Is it a subgroup or a subgroup?
So if H is a subgroup and G is an H, then this thing is a subset here. Let's prove this, okay?
Yeah.
So what is the cyclic subgroup generated by G? Is the set of all possible powers of your element. Okay?
Okay.
So by the definition of H, it contains 1. So good for this element. So it contains G. So we don't care about this element. Now, since G is in H, then G times G is also in H.
Okay,
so,
and that's for all the powers. Okay, I see.
Yeah, then also we have G minus 1 in H also by the definition. So we have this element and so on.
Okay, now I see, thank you.
Yeah, we're doing this by the brute force. We're just considering all possible subsets and use the fact that if we have an element in the subgroup, then the whole cyclic subgroup generated by this element is in our subgroup, and so on. So now we're here in this place. So we consider the case where our subgroup H contains at least one non-identity element, which is this, or this. And in this case, we have this inclusion. And I considered only one possibility when this inclusion is equality. This leads to these 4 cases, 3, 4, 5, and 6. So do you have any question regarding this part of the proof? Okay, so now we're in a position where we have, for example, this case. So we have this subgroup generated by 1, 2 in H, but also this is a strict inclusion. So there is at least one new element. And there are like several options, like it's either these elements or these elements or the other elements. So now we should show that if at least one of the other elements is an H, then H is equal to the whole group S3. Well, for example, if the element 2, 3 is an H, 1, 2 is an H, then there must be this product in H, which is 1, 2, 3. So this guy is an H. Then the inverse to the element 1, 2, 3 is an H. And actually, if you multiply, so then 2, 1, 3, it must be an H. And then you just multiply this element to this guy, and this gives you element 1, 3. I did this in a very quick manner, so if you lost, just tell me. But what I did here, my claim is that in the in case when our subgroup H strictly contains one of the cyclic subgroups listed here, we should show that H must coincide with the whole group. How we do that? We consider the cases. Like, for example, we contain this subgroup, and we also contains an element which is not here. For example, these, and for this element, we just start producing different products, inverses of the new elements, and get all possible elements of S3 and show that they belong to H. And this was an example of the computation, how to get that. Was it clear? Should I explain here in more details, or you think you can do it by yourself if you need? No questions mean there is no question, or you're undecided regarding how to do?
I think there are really no questions then.
Okay. Okay, that's nice. So we have 5 minutes. Let me see. I think I have one good problem for you. So let's consider a very specific group. So the question must be simple, right? Simple question. For a simple question, we need a simple group. So let's G be GL2 of R. So just 2 by 2 matrices over non-degenerate matrices over real numbers. Could you give me an example of an element G here such that its order is 13? Probably it's a quite complicated question. Let's start with a better question. Its order is 1. Its order.
What operation do we use?
Multiplication. GLN always mean multiplication.
Oh, okay.
So yeah, that's a good point. Yeah, of order 1 is just the identity matrix, which is 1, 0, 0, 1. An element of order 2.
It will be identity matrix multiplied by 2.
Identity matrix transposed is the identity matrix. It doesn't
No, like yeah. 2, 0, 0, 2.
This one, 0, 1, 1, 0.
No, 0, 2, 2, 0.
Okay. 0, 2, 2, 0. Oh. Well, 0, 2, 2, 0 doesn't work here.
I mean, no, 0, 2, 0, 2. Like identity matrix multiplied by 2. Oh, it's still wrong, yes.
Yeah.
I
So-
understand why it's wrong.
You see, yeah?
Yeah.
Because all powers of this guy will have like greater powers of 2, like 2 to the like 4, 8,
Like 4, yes, it's 16, 32.
yeah, or 1/2, 1/4, 1/8, etc. So you will get identity only for 0 power. So this element has order infinity because all powers of this element are distinct. And this guy is actually of order 2. So it's not the identity, but its square is the identity. Okay?
Yeah.
Could you find an element of order 3?
0, 1, 1, 1.
0, 1, 1, 1. No, actually. 0, 1, 1, 1 doesn't work because let's multiply it several times. Well, identity to the power of 3 is not the example because identity has order 1. So identity to the power of 3 is again identity. So your Maxim, your example is just identity matrix, but identity has order 1, and we want it order to be of order 3. So the order is the minimal possible power, positive power, where the matrix becomes identity. But the identity to the power of 1 becomes identity, not just 3. Okay. So, and I'm saying that, okay. So
We just need to
So, I mean, this is the wrong example. So if you compute this third power, it doesn't work. Let me help you. So how do you?
we should. I understand how to do it. We should just consider like inverse of this matrix and calculate. We know this algorithm.
Let me explain. Yeah. Well, so that's a good question. How can we solve this problem? So where do we get our example? So here you should ask another question. How should you think about GL2? What is actually GL2? Well, you should think about GL2 as the set of non-invertible linear transformations. Linear transformations of the plane. Wrong word. Of the plane. So, yeah, we can consider rotations then. Yep. So now, when you think about GLN in a...
Wait a moment, I need a few minutes to calculate this.
What again?
I know, so I just need a minute to calculate it.
Still cannot hear you. It's... Okay, so now, when you think of GL2 as the set of linear transformations, invertible linear transformations, you know that there is a rotation transformation. So you take the rotation by the angle 2p over 3, and it's given by the matrix, which looks like this. And this is...
It will be still...
Is it clear? So if you do this rotation, so its second power will be rotation by the angle 4p over 3. So it's still not identity operation. But if you consider its third power, it will be rotation by the angle 2p, which is the same as the identity doing nothing. So the third power will be the first power making this matrix to be identity. Is it clear? Do you have any questions considering this example? Okay. Now, can you answer the initial question? Could you give me an example of an element of order 13? Yeah. That's rotation by the angle 2p over 13. That's it. Okay, guys, we're out of time. I hope.
Sir, will you share with us this, I don't know how to call it, slide or what?
What again?
Will you share with us this picture, I don't know how it's called, slide or what?
Oh,
This hand drive.
yeah, I will post all the whiteboards. They will be in SVG format. It's a vector graphic format. So you will be able to open them in any browser.
Hmm.
For example,
Very much.
Chrome. Okay, so do you have any other questions?
No?
Okay, if not, then thank you guys. Hope you enjoyed, hope it was fun, and I hope it was also useful and you learned something. Well, see you next time.